Welcome to this latest installment of the recent advances in organic chemistry research in academia through the use of real-time in situ FTIR series for 2010. I'm going to do something a little different than what I've done in the previous installments. In the past, I tried to go into some detail on 3 or 4 recent publications to really give a good overview of the research conducted, and then to show how real-time in situ FTIR, in addition to other analytical techniques, provided information that contributed to the advancement of the research. Today, I'll cover a broader range of papers, going into less detail with the hope of conveying the broad scope of application for in situ FTIR in academia. From January until November in 2010, there have been 28 publications in the ACS journals alone, with 22 of those coming from academia. What is clear from the list of journals represented is that in situ METTLER is used across a very wide range of chemical research. On October 25, 2010, an award article was published in Inorganic Chemistry by Professor Donald Darensbourg of Texas A&M University. According to my research in ACS journals alone, Professor Darensbourg has cited the use of FTIR in 26 publications. Professor Darensbourg is a longtime user of in situ FTIR and has used FTIR technology since 1999. A typical configuration that he uses is shown above, where a high-pressure probe with a silicon sensor is mounted directly into the bottom of a PAR autoclave vessel. To quote from the article, as indicated in Figure B, this procedure for in situ monitoring of the epoxide CO2 coupling reaction provides real-time data for the formation of both copolymer and cyclic carbonate reaction products. For the two commonly studied allocyclic and aliphatic epoxide, CHO and PO, we established that at the reaction conditions of 80 degrees C, the two epoxides were selective for affording polycyclohexylene carbonate and polypropylene carbonate, respectively. Upon a decrease of the reaction temperature to 30 degrees C, the reaction between PO and CO2 selectively provided polypropylene carbonate. Temperature-dependent rate data obtained via in situ IR spectroscopy studies for the coupling reactions of CHO or PO with CO2 have provided energy profiles in their research for the formation of the two products, copolymer versus cyclic carbonate. Darensbourg has also used FTIR extensively for reaction kinetic studies. Shown here, for example, is a comparison of the catalytic activities for the copolymerization of CHO and CO2 using the two closely related complexes carried out under the same reaction conditions. These observations have been used to support mechanistic theory. In Part 5 of the Recent Advances series, I covered this research in more detail. This data represents the copolymerization reaction of oxetane and CO2. In situ FTIR was used to provide concentration profiles for copolymer and TMC formation with time. This information allowed the observation that the formation of TMC is enhanced at the early stages of the coupling reaction and that its concentration decreases rapidly over time, but that the concentration of poly-TMC was initially inhibited, followed by rapid increase over the course of the reaction. In situ FTIR provides critical information of reaction kinetics under elevated temperature and pressure in a natural environment without perturbing the reaction. This is normally not possible using offline analytical techniques. This next article comes from Professor Bernhard Rieger at the Technical University of Munich, which was published in the ACS Journal of Macromolecules on the web on October 22, 2010. Their research is on polyhydroxybutyrate, PHB, a naturally occurring aliphatic polyester that is produced by a variety of bacteria and microorganisms as an internal energy and carbon reserve, and thus features biodegradation and biocompatibility. PHB is an important biopolymer for a variety of reasons, but is currently only manufactured through biotechnology. The bioengineering route to PHB is expensive compared with the chemical synthesis of commodity polymers. To compete with respect to price, a synthetic pathway to polyhydroxybutyrate of controlled stereoregularity from commercial available starting materials is required. The authors report on a study of the south-end catalyzed ring-opening polymerization of beta-butyrolactone, including the investigation of electronic and steric effects within the ligand, as well as of the influence of different reaction components that control the polymerization. Kinetic studies using a catalyst of known activity were performed to verify the reaction mechanism. To quote the authors, online FTIR spectroscopy has been shown to be a useful tool to get a direct insight into a reaction. Using this technique, the polymerization can easily be followed by a linear growing polymer signal at 1744 reciprocal centimeters after a short latency period due to initiation mechanism." End quote. As is usually the case, other analytical techniques are used as complementary data sets. In this case, proton NMR and in situ IR were used to provide kinetic information that was then used to determine reaction order. In situ FTIR is particularly powerful because of the number of data points. Typically, the data acquisition rate is 1-minute intervals or less, so one experiment can yield hundreds of data points. Kinetic software, such as our recently introduced IC Kinetic software, can take advantage of these data-rich files, drastically reducing the number of experiments needed to obtain the information needed to determine rate law equations confirming reaction orders. This next article was published in the Journal of Inorganic Chemistry as well. However, as it involves organic chemistry, I thought it had a place here, and it's a good example of yet another application for in situ FTIR. It comes to us from Professor Chiang of the Institute of Chemistry in Taipei, Taiwan. The researchers used in situ mid-IR during electrocatalysis to monitor the hydrolysis of acetic acid, to confirm that the catalyst did not deplete, and to monitor the formation of the reduction product. Much more spectroscopic information can be found in the supporting information. The fourth article was published in July 2010 in Organic Letters and comes from Jason Kingsbury of Boston College's Department of Chemistry. Building upon their interests in the study of non-carbonyl stabilized diazo alkanes as carbon nucleophiles in synthesis, the researchers have begun to explore the regiochemistry of carbon insertion under conditions of true catalysis. They reported a TMSD-based ring expansion of aryl butanones that proceed with high regio control. Quoting the authors, closer analysis of the reaction pathway for the homologation of ketone 1A was revealing. As shown in Scheme 2, real-time monitoring of the event by FTIR spectroscopy confirms a short-lived 1-hour intermediacy of beta-ketosiylane 13, whose carbonyl stretch at 1717 reciprocal centimeters is easily discernible from that of the starting 1A at 1775 reciprocal centimeters. End quote. The use of in situ FTIR to monitor reactive intermediates is a common application and is one, as is in this case, that can provide critical reaction mechanistic information. Note that this reaction is conducted at 0 degrees C, so it is probably not possible to detect this short-lived intermediate species by offline analytical techniques. Research Article 5 was published by Clark Landis from the Department of Chemistry at the University of Wisconsin at Madison in the Journal of the American Chemical Society in July of 2010. Asymmetric hydroformylation is an efficient, low-cost route to chiral aldehydes from prochiral alkenes. However, practical applications of asymmetric hydroformylation faces several challenges. Production of a single branched aldehyde with high enantiomeric purity requires precise control of chemo, enantio, and regioselectivity. Large-scale applications require high catalyst rates and large turnover numbers, particularly when expensive metals or chiral ligands are used. Asymmetric hydroformylation of terminal aryl alkenes exhibits complex behavior as a function of the gas partial pressure. Increased CO pressures yield higher regioselectivity and enantioselectivity, but suppresses the rate. In contrast, changes in hydrogen pressure have little influence. The researchers sought a better understanding of the origin of regioselectivity and enantioselectivity in asymmetric hydroformylation. As is with many of the examples we have seen here, REACT-IR was used to determine reaction kinetics. In this case, hydroformylation rates were shown to exhibit a linear dependence on catalysts and alkene concentration. The effect of catalysts and alkene concentrations on hydroformylation rates is depicted in the figure shown. A plot of the initial rate of aldehyde formation versus catalyst concentrations, 0.2 to 2 millimolar, indicates a first-order dependence on catalyst concentration. The reaction order with respect to alkene was determined by monitoring the entire reaction time course using in situ infrared spectroscopy. As shown here, the formation of aldehyde exhibits a well-behaved first-order dependence on alkene concentration. A solution of rhodium catalyst, styrene and toluene, was placed in a high-pressure reaction vessel fitted with an in situ attenuated total reflectance mid-infrared probe. The vessel was sealed under nitrogen and removed from a glove box. The autoclave was then heated to 80 degrees C, followed by pressurization with syngas, 1:1 CO hydrogen. With rapid stirring, IR spectra were collected every 2 minutes. Recording was started 30 seconds before the addition of syngas, and the appearance of aldehydes was monitored as the change in intensity of the absorption peak centered at 1725 reciprocal centimeters, which corresponds to the overlapping carbonyl stretching frequencies of the branched and linear aldehydes. There are several things to point out here. The first is that the reaction is under relatively high temperature and pressure, which makes it difficult, if not possible, to get accurate information by offline analysis, as we have seen in a couple of the other examples. The second is how rich the real-time in situ data is in information. Initial rate experiments on the left indicate 4 experiments were performed, resulting in 4 data points. In situ information on the right was collected at 2-minute intervals, resulting in 120 data points from one experiment over a wide range of synthetically relevant and changing component concentrations. The sixth and final example from the literature was also published in July of 2010. It comes from David McMillan at the Merck Center for Catalysis at Princeton, in Princeton, New Jersey, and was published in the Journal of the American Chemical Society. The mechanism of a recently reported aldehyde alpha oxyamination reaction has been studied using a combination of kinetic, spectrometric, and spectrophotometric techniques. Most crucially, the use of a validated cyclopropane-based radial clock substrate has demonstrated that carbon-oxygen bond formation occurs predominantly through an enamine activation manifold. The mechanistic details reported in this article indicate that as has been proposed for previously studied alcohol oxidations, complexation between TEMPO and a simple metal salt leads to electrophilic ionic reactivity. I found the following information in the supplemental information for this research article. The researchers were initially concerned that ferrocenium may reversibly form a complex with TEMPO, as such an interaction would alter the concentration of free TEMPO in solution, possibly inducing error into their radial clock investigations. They turned to REACT-IR, which allowed for the direct observation of TEMPO in solution at the concentration the reaction is performed, 2 molar. A REACT-IR probe was immersed in 1 ml of pure THF to allow for the collection of a solvent background spectrum, and a 1-hour experiment was initiated with data points collected every 30 seconds. After 3 minutes and 30 seconds, the experiment was paused. TEMPO, 315 milligrams, 2.02 millimole, was added to the THF solution, and the experiment was resumed. Of all the new peaks observed, the maxima found at 1471 reciprocal centimeters and 1363 reciprocal centimeters were both the most intense and occurred at the position further away from the significant THF absorbances and were therefore used for analysis. After 6 minutes and 30 seconds, the experiment was paused and ferrocenium, 327 milligrams, or 0.99 millimole, was added to the solution. The experiment was then resumed and continued undisturbed until 1 hour had elapsed. The addition of ferrocenium caused no change in either the position or intensity of the maxima at 1471 and 1363 wave numbers." End quote. This is a very straightforward application for in situ FTIR, but I think it clearly highlights the fact that sometimes the only way to have confidence in your data is to look and literally see what happens under natural reaction conditions. I would like to conclude by making some observations about the examples we saw here for the use of in situ FTIR in academia, and also based on my past experience with the use of FTIR in academia and sometimes in industry as well. First, the information contained in real-time in situ FTIR data provides outstanding value really across a wide range of applications. This is proven not only by the few examples I have shown here, but by the nearly 1,000 or so research articles that have been published worldwide citing the use of REACT-IR alone. Of course, in situ FTIR is not the sole analytical tool in really any of these articles. I intentionally focused on the information that REACT-IR provided. But the key is to use the information to complement other analytical techniques. I can say from experience that many times in situ FTIR provided that critical piece of information that allowed the researchers to focus their research in the right direction. A couple of the examples today showed us how easy it is to get accurate information in situ and in real time from reactions that were under pressure, at extreme temperature, or both. Any kind of extreme reaction condition, which can include toxic or hazardous conditions, makes the collection of information automated, eliminating not only the perturbation or disturbance of the chemistry, but also having to come in contact with it, particularly valuable. As we can see here, using REACT-IR is a natural for kinetic studies. REACT-IR data is extremely comprehensive, as I've mentioned before, which leads to more kinetics information in less experimental time. Instead of running 20 or 30 experiments to get initial rate data across a range of concentration, many times the same information can be extracted by conducting 2 or 3 carefully designed experiments. This is easier than ever to achieve now that specific software as I mentioned earlier, IC Kinetics, has been developed by us to directly import and automate kinetic analysis of ReactIR data files. I'll finish with a comment that is more anecdotal than anything else, and that is, the more you use in situ FTIR, of course for me meaning ReactIR, the more you come to realize how indispensable that information is. David Collum from Cornell University once told an audience at a conference I attended on process development chemistry that when he is consulted by industry about a problem they are experiencing with some particular synthesis, that he always asks, "What did the ReactIR tell you?" And if they say they didn't look at the chemistry with ReactIR, he asks, "Why not?" So Professor Collum is a longtime user of ReactIR technology and clearly has come to realize how important the information is. I find the same realization to be true across not only academia, but in industry, where those who use the tool routinely get the most value from it.